Hi, my name is Danny Iland, and this is a presentation about using delay-tolerant networks in disaster scenarios. And in particular, it's going to outline the disaster app that myself and Don Voita have created for the OLPC project as part of a mobile computing class at UC Santa Barbara. And I want to start with something that happened just 2 days ago in Mexico. There was a quite strong earthquake with an epicenter near Mexico City, and this photo is on the front page of the LA Times, and it really shows how immediately after a disaster, the entire population is feeling pretty much the same thing, which is uncertainty. And these people here, they're obviously observing something happening, they're trying to contact either someone who can help or someone close to them, but the internet is knocked out, there's no electricity, there's no phone service. So this time, immediately following a disaster, is when much of the important information for responding to that disaster is created. So that's the concept of that we're trying to address here. And when we're developing for a disaster, we have to consider what's worked in the last several years, and that has been, in my view, Ushahidi. So Ushahidi is a crisis mapping platform. If you're watching this, I'm sure you've at least heard of it. And it's been used to great effect in disasters like Haiti on the left here, and in Pakistan following the flooding there. And Ushahidi relies on Twitter feeds, direct text messages from people on the ground. They do more conventional information collection, such as listening to the radio. But a lot of the main use, I believe it was something like 30,000 messages in 1 month in Haiti, came from SMS. And immediately following a disaster, this SMS infrastructure just may not be present anymore. So what we want to do is really take advantage of the fact that almost every user now has a mobile device, and more these mobile devices support Wi-Fi. And we believe that these Wi-Fi devices should be configurable in ad hoc or mesh modes to use epidemic message passing. And if you don't know what epidemic message passing is, basically imagine your information and your knowledge is a disease. And when you come into contact with another device, you give that other device all of your messages, all of your information, and in turn they do the same. And we implement this on the OLPCs, so any child can write a message with their location, a description of what their crisis or emergency is, and the category. And then these messages are spread via Wi-Fi with a shared activity from XO to XO. And if any of these XOs reaches an area with an active internet connection, it can upload all of the messages that it carries to an Ushahidi Crisis Map. And So one problem with this kind of scheme is there's a lot of network congestion because messages are replicated. There are many copies of every message throughout the network. And after a message has been received by Ushahidi, by the server, we want to notify the sender that this information has been received. And we also want to notify the other nodes in the network that they should stop trying to send this message because it's already been received. So for that we use what's called a cure, which is just a time-stamped message hash. So we built two things over the last 2.5 months roughly. We've built a shared activity for OLPC, and this shared activity is a pretty standard Python PyGTK activity, just like many activities on OLPC, and because of that it uses telepathy salute and dbus for communication between XOs. and it follows the same UI characteristics of any shared activity. In the neighborhood view, you can see other XOs if they are also sharing or in public mode. You can join their activity, and then you'll get any messages that anyone in that group sends. And as we've said, if as soon as an XO has internet access, all of its messages are uploaded to the crisis map. And this plugin, we have designed it to be just a drop-in plugin, just like any other. So if you run an Ushahidi server right now, you can install this and receive messages from any child with an XO. And we really hope that we can get partners who would like to try this program out for messaging within their community, messaging from a non-profit organization or any organization outside a community that wants to reach the children in the community and their families. I'll put in a YouTube video on this post that will show you how this actually works on the XOs. And we have a small demo server set up that we've been using for testing that just is in the UC Santa Barbara area, and that looks like this. So this is our small Ushahidi install, and as you can see, we've implemented geotagging. Whatever location string someone enters in the application, it will find the coordinates using Google Maps geocoding. And during our testing, we generated several thousand messages to evaluate the effectiveness of this sharing scheme. So this is the testing we've performed. We generated 100 and 500 messages, each about 500 bytes, which could be a several paragraph message or a small photo. And we measured the battery consumption of the devices, and also we measured all network traffic that was generated by our devices. And we also did a nice outdoor range and mobility test to see how feasible this is, and what density of XOs would be required to have an effective network, and I'll get into that in a bit. So one problem that we have identified so far in our solution is that the use of telepathy salute introduces significant overhead. And you can see this clique overhead labeled on the graph. And so the column on the right here represents our actual data, the messages that people in the system have created. So as you'd expect, the red bar shows that most of the data being transmitted in this network is the data people have produced. However, you'll notice that almost the majority of the packets in this network are actually overhead packets from the clique protocol. And clique is used by telepathy salute, and it just produces many small packets. It's not very well suited to this kind of application. So moving forward, we're going to try and replace telepathy salute with a more efficient protocol. And when we increased the number of messages that we were sending, this problem only became more pronounced. So having almost 90% of packets being overhead packets was really, it made the network very slow to converge, and message sending was quite slow. And we also showed that battery consumption and throughput, or wireless radio usage, are directly correlated. So we weren't sure if just how important it was to reduce our wireless usage, but we have shown that we can improve the battery life. For every packet we don't send, basically, we can save a few milliamp hours of battery usage. So this is our outdoor tests that we ran. Along the bottom here you can see our first test, which is on the nice beach bluffs at UC Santa Barbara, and we were able to get a 1100 foot Wi-Fi range between these two nodes. And we were quite happy with that. There was were very few sources of potential interference in that test. So we believe that's pretty reflective of a rural area. And in this test here, it's a little more complicated. We set up a node and had it transmit through buildings, trees, brick walls, to represent more of an urban or campus setting. And the Wi-Fi range with that transmission was maxed out at about 330 feet. And then you can see this long grassy lawn. We were again able to get the 1100 foot range with line of sight. And we had an XO in this location. We moved it to be in this courtyard here, and from that courtyard it was able to communicate wirelessly with the XO labeled 6 here, which was in our office in Harold Frank Hall. And that XO was directly connected to the internet. So for example, this could be a hospital that has a wireless satellite internet connection, or really any internet connected place. And the node 6 here was able to download the cures and upload all the messages. The cures are passed back to node 5 here, and when he walks back into range of our original sending node, those cures are delivered, and these two individuals know their messages have been received. So I'm quite happy with the development of this app so far, but I really want to keep going and make this project really have a lot of value for XO users. So something that's helped us a lot in the project was the groupthink library, and this is basically enabling apps and activities on the OLPC XOs to use shared data structures. And we'd like to extend groupthink to use delay-tolerant syncing. So if you create a shared data structure in groupthink, and you compose a message to someone in your group, even if they're not present in the group, we'd like to try to send that message from XO to XO until it can hopefully reach the intended recipient. So that means using the existing, basically, when you use the OLPC XOs command at the command line, you get a list of all XOs on the network. We can build a network of XOs that all participate in the same groups or messages. For example, students in a classroom, groups of friends, and allowing them all to collaborate within their group with delay-tolerant message passing through the entire network of XOs. This could be really cool, and it really goes directly towards our disaster scenario as well, if you consider the entire community to be one large group. And we also want to address issues with literacy and usability, and in particular that means enabling audio and photo uploads. And we'd also like to make this compatible with applications on Windows PCs and Android phones. So I hope that you've enjoyed this presentation. If you have any questions, please email me or call me, and my contact information is posted. Thanks, I'm Danny Iland. Bye.